how to quantize this, how to make this acceptable for quantum mechanics. So we have what's called out of phase rotation and in phase rotation. So if I look at the out of phase rotation, okay, so for example, suppose on my first circuit, right? So imagine I'm taking my particle right round, baby, right round. We're spinning it around. So what I've got here now, this is the particle's circuit, but plotted linearly, like spread out on a linear graph, okay, given by the radians, right? 0, pi, 2 pi for a full complete circuit, right? 2 pi for a full circuit, okay? So if I start at 0 and I end up here, you know, halfway, that's pi. And then if I go around the other half, right, I get to 2 pi, okay? So on this quantization, if let's say I start here on the first circuit and I'm going through this first circuit and I'm going, you know, as a wave through this circuit right here, and I finish my 2 pi full loop circuit down here. Well, then look where I start the next circuit, right? I go all the way up and I start the second circuit right here. Well, you can see right away that's going to be problematic because my Schrodinger, my wave function has to be single valued. And so as I go and make successive loops, successive circuits, you can see that it's not single valued, right? It's a double valued function. So that's what we call out of phase rotation. So what we have to do instead, we have to have in phase rotation, where if I start up here and go through my first full circuit from 0 to 2 pi, I have to end up where I started. Because now when this goes to its next loop, it's gonna be single valued, okay? So this is our main boundary condition requirement in the particle on a ring problem, is we have to have in phase rotation. So due to the requirements of acceptable solutions to Schrodinger, only certain JZ values are acceptable. So in other words, to maintain this in phase rotation, it's really going to be all about the angular momentum. We're going to fix the angular momentum to give us that in phase rotation. Okay?